So let's look at what happens if you use the polar transform along with a channel. Okay. So here's an example. I've shown 8 bits here. 8 could be any n. I've used n equals 8 for illustration, but it could be any other n. Okay. So you have 8 bits coming in. You use the polar transform G8. You get 8 outputs. Okay. So these outputs could be anything, and usually you can denote it as x1, x2, x3, x4, x5, x6, x7, x8. So these are 8 bits, and then you can transmit them through BPSK AWGN. What is BPSK? Once again, 0 goes to +1, 1 goes to -1. And what's AWGN? It's S plus noise, right? So noise is normal with mean 0 and variance sigma square, some sigma square. So you create this noise, you get received values. Okay. So this is how a polar transform could potentially be used in the BPSK AWGN channel, and then this Rn is the received vector. This is just notation for the received vector. Okay. It's fine, we used it, it's just an invertible transform, but why would you use it? What is the point of using a polar transform before a channel? So it turns out, if you don't use the polar transform, every bit sort of goes through the same channel in some way. Okay. So there's nothing much maybe you can do. The polar transform combines these bits and gives us one some sort of a reordering, or changes the channel in some way. You can view it in a different way. Okay. So this notion of looking at individual bit channels after the polar transform is the key innovation in polar codes, and it turns out those channels vary a lot in terms of quality. Okay. So that's the next picture. So this picture is easy enough, there's nothing much going on. You have so many bits coming in, you do the polar transform. You can do it for any n, right? I've shown it for n equals 8, you can do it for n equals 1024 also. You have 1024 bits coming in, you hit it with the polar transform, you get outputs, you do the BPSK AWGN, you get received vector. Okay. Now what is the effect that this has? How do you view this in a polarization point of view? Here is the picture. Okay. So this picture is the central idea behind polarization. Once again, we will not go deep into the theory of this picture, except that we'll present that from a high level to understand what's going on. Okay. So it turns out, after polarization, you can sort of decompose or view what has happened in terms of what's going on to the individual bits in a sequential way. Okay. So you can convert the n channels that you had into n combined channels that you had in the polarization after when you did polarization, and split them up sort of into individual bit channels. And the first bit channel is defined as follows. You have E1 going in, this is the input to the first bit channel, and the output is the entire received vector Rn. Okay, remember once again, the entire received vector. This is the first bit channel, split bit channel. This is just a definition at this point. Okay, I am defining the first bit channel to have U1 as the input and the entire received vector as the output. Okay. So I'm reordering or viewing the previous channel. So in the previous picture we had this kind of a picture. I am seeing this in a different way. Okay. Remember, I've got all the bits, all the received values at the output. Okay. And remember, the first bit would have affected all these bits in some way. So all the received values will have some information about the first bit. Okay. So it's not wrong to view it this way. Okay. So we'll take input as U1, and the bit channel, I will imagine, has a huge output, has all the outputs together, the entire received vector collected together, that's the output. Okay. Now I'll define sort of a second bit channel which has input as U2, which is the second bit, but look at the output here. Pay attention particularly. The Rn is fine. Okay. So you might say the entire received vector is there, but to this I will add U1 as one of the outputs of this bit channel. Okay. So now at this point, this is not a real output. Okay. Why is that? Because the channel is not giving me U1. Okay. The channel only gives me Rn. Okay. I will imagine that somehow I have this U1. Okay. And we will see how to create this U1 in the actual physical channel. It turns out you can create a good estimate for this U1 in some way and cleverly use it and get this effect of channel polarization. But at this point I am defining the second bit channel as input U2 and having output as the entire received vector and the previous bit U1 as one of the outputs. Okay, it's just a definition. Next comes the third bit channel. So here I'll go even little bit further. Okay. So, I have the entire Rn as the output, U3 is the input again. Okay. Entire Rn is the output. Along with that, I will say both U1 and U2 I already have at the output. Okay. Once again, these are not real outputs at this point, but just carry along with me. We will see later on how to get some substitutes for these U1, U2 later on. For now, U1, U2 will imagine somebody is giving me at the decoder. Some benevolent person is giving me what U1 and U2 are, and I am imagining this second, third bit channel. So, likewise you can proceed. What do I do for the ith bit? For the bit channel I will imagine that the entire received vector is there. That is not very hard to imagine. I have the entire received vector. But then I will also imagine I have all the previous bits that were transmitted. So, U1 to Ui minus 1 I already have at the output. This will be what I will imagine. Okay. So, likewise I will go all the way up to the nth bit channel, which has all the received values, that is okay, and then all the previous bits. Okay. So, now what is special about this split channels? What is special about these bit channels is these bit channels are not similar at all. Okay. They are very different from each other if you view the whole picture, they are all very different in quality. In the previous case, all the channels here, all the channels for which you received R1 are the same. Here, these n channels will have very different behavior. Okay. So, you can imagine why, right. So, first of all, these channels are very different from the previous channels. Okay. They have 1 bit input, but the outputs are huge. Okay. And also you are assuming the previous bits are available. So, they can be very different in quality, and that is true. Okay. So, it turns out you can study these bit channels very carefully, and you can sort of order them based on quality. Okay. And the quality you can show varies a lot from very good to very bad. Okay. And it turns out as you increase n, they either become very good or very bad. There are literally no channels which are sort of mediocre. Okay. Neither very good nor very bad. Okay. Nothing in the middle, no middle path. All the bit channels either become very good or very bad. So, this is the essence of polarization. What does polarization mean? You either go to the north pole or the south pole, right? Polarization, one of two things, nothing in the middle. Okay. So, that way these bit channels get polarized. Okay. They either become very good or very bad. Okay. So, these are called this is called polarization. There is a wonderful information theoretic proof for this polarization, for what type of channels it happens and all that. And once again, we will not study that, at least in this course. Maybe later on we will add some additional content for this. But for now, we will just look at how to use this polarization to define polar codes, and how to use this polarization to design decoders for polar codes, okay, and achieve good performance. That will be the focus of the lectures in this course, but this idea is very central. But keep note of this, not having the real output, and what do we do for that? We will postpone this discussion when we come to the decoder. For now, we will use this idea of polarization and start talking about how to define polar codes. Okay, we will come to this notion of how to recreate this U1 at the output side later on. Okay. Okay. So, now the next important idea is that of a reliability sequence. Okay. So, I mentioned how after polarization, if you take the bits, you polarize them and transmit them one after the other on the BPSK AWGN channel, there is a lot of polarization. Okay. Some bits become some bit channels, and then you can define these clever bit channels which have previous inputs. If you do that, then some channels become very good, some channels become very bad. Now, which channels are good, which channels are bad? Okay. That is given by the reliability sequence. This tells you the ordering of channels, ordering of bit channels from worst to best. Okay. Which is the worst among these n bit channels, and which is the best among these first bit channels. I am giving you the reliability sequence as per the 5G standard. Okay. Now, there are multiple ways to create this reliability sequence, and there are lots of research going on, and how accurately you can find the reliability sequence, how realistic it is, etc. All of that we are not going to go into great detail, but we will simply provide the final answer. Okay. So, it turns out for n equals 8, according to the 5G standard, the reliability sequence is this. Okay. 1, the bit channel 1 is the worst channel. Next comes 2. Okay. After that is 3. After that is 5. After that is 4. Then 6, 7, 8. Okay. So, it is not the same order as 1, 2, 3, 4, 5. So, you see this 2 got switched for n equals 8. Okay. So, the 4th bit channel is better than the 5th bit channel according to this reliability sequencing. Okay. So, like I said, the way in which you do this is not very precise. It's sort of, it involves some simulations and all that. Maybe I'll point you to some references in if you are interested in reading about how to find this reliability sequence. But in these lectures, we won't focus on how to find this reliability sequence. We'll just think about how to use them for designing, for encoding and decoding polar codes. Okay. So, here is the reliability sequence for n equals 16. So, you see this 1, 2, 3, 5 comes again, and then suddenly 9 comes. Okay. 9 becomes a bad channel, then you have 4, 6, 10. This is the sequence. Okay. So, for instance, 14th bit channel is better than the 12th bit channel. The 8th bit channel is worse than the 12th bit channel, like that. That is how you read it. This is the sequence in which the quality of the channels is ordered. There are 16 bit channels, they are ordered like this. This is for n equals 32. Remember, all these numbers, like I said, I am pulling from the 5G standard. The 5G standard specifies this for n equals 1024. Okay. And sequence for smaller n is derived from the sequence for n equals 1024. Okay. So, I am just picking it up from there. Okay. So, you can also do this if you have access to the 5G standard. You can go pick up the reliability sequence for 1024, and then from that find the subsequences which are for n equals 8, 16, 32 and all that. Okay. So, what is the final summary? Once you do the polar transform and transmit on the PPSK AWGN channel, for instance, or any other channel for that matter, we can take a global sort of reliability sequence, the bit, and then create these bit channels. The bit channels become polarized, and they can be ordered from the worst to the best, and the sequencing is sort of given here. Okay. You can take one sequencing. How do you find the sequencing? We are not going into details there, but the final answer is given to you. Okay. So, this is the sequencing. All right. So, this is the notion of reliability sequence. It is very crucial for designing and defining polar codes. It is very important. Okay. So, here is the full reliability sequence for n equals 1024. I am not expecting you to learn this by heart. You do not have to do this. You do not have to mug up this sequence, but this is the sequence. It's given in the standard, and you can see how it goes. There's no pattern here, right? So, it's sort of random in some sense, but not all that random. It sort of increases from 1 to 1024 in some generic way, but suddenly you will have some big numbers showing up in early on, right? So, it's sort of difficult to predict. There's no real pattern here, as far as at least I know. There's no pattern here. It's hard to come up with these estimates, and also you might, if you read more, you will see if the noise variance changes in the AWGN channel, this reliability sequence actually changes. Okay. So, it actually changes. So, it's hard to pick up one reliability sequence for a wide range of noise variances, but people use some close simulation studies and carefully study it and come up with something like this. Okay. So, the reliability sequence is a difficult thing to find. Okay. It's not very easy to find. There are good methods available today in the literature, but like I said, even if you find it, strictly it will vary from noise variance to noise variance, and it's not sort of contained. For many cases it's not contained, some cases it's contained. So you can use some approximations, and there is a structure, but it's a very hotly researched topic today. Okay. So, reliability sequence is important, but for us we are not going to focus too much on the difficulties around the reliability sequence. We will simply take the one that's given in the standard and be happy about it. Okay. So, if you are doing that, there's no problem. Okay. So, having done all this work, having studied the polarization, having studied these bit channels, having understood what the definition of this reliability sequence is, we are ready to define the polar code. Okay. So, nk polar code is defined for n equals 2 power n. Okay. And the small n could be, usually you want to start at 4, 2 at least, 2, 3, so on. Okay. The message m is of length k bits, and this k is going to be less than or equal to n. Okay. Message m is of length k bits, that's okay. What do you do to define the polar code? I will define the encoder for polar code. Okay. This is the encoder for the nk polar code. I will form a vector u of length n bits. Okay. How do I form that? I will first find the n minus k least reliable or worst channels from the reliability sequence. Okay. There is a reliability sequence. What is the first n minus k least reliable? The first n minus k numbers in the sequence is the least reliable, right. So, you take the n minus k least reliable, and I will set the ui for these n minus k channels to 0. Okay. So, I am saying channels here, remember these are like n minus k positions. Okay. The first n minus k least reliable positions as per the least reliability sequence, you set those ui to be equal to 0. Remember ui has length n. Okay. The first n minus k positions, whatever they are, you set them to 0. Okay. The ui corresponding to the first n minus k positions in the reliability sequence. Remember, it is not in the same order, the order sometimes changes. You set those to 0. Now, there will be k remaining positions for u. Okay. The k remaining positions, you set them to be equal to the message. Okay. All right. So, you have this vector u. Okay. It has n positions, 1, 2, so on till n. Okay. The n minus k least reliable positions, you put 0. Okay. So, you will put 0 here, you put 0 here, wherever they are least reliable, you put 0. Okay. And then the remaining guys, you put message. K most reliable. So, least and most are with respect to the reliability sequence. Okay. So, there you put your messages go there. Okay. So, you form a vector u like this, and then what is the code word? Code word is simply the polar transform of u. Okay. U times Gn polar transform of u. Is it okay? That is the definition for the nk polar code. For any n you can do this. Once you have a reliability sequence, you have a polar code, right. So, it is as simple as that, right. So, hopefully this is clear. We started with the 2 by 2 polar kernel, we created the Gn polar kernel, then we looked at the polarization property, and then we defined the reliability sequence. Once you define the reliability sequence, you have a polar code. Okay. So, that is it. Here are a few examples. I am starting with n equals 8, small n equals 3, okay, and defining the 8, 4 polar code. This is the reliability sequence. So, the frozen positions, the ones for which you choose them to be 0, these are called the frozen positions. Okay. So, once again I think I missed defining that. The least reliable n minus k least reliable channels which you set to 0 are called the frozen positions. Okay. And then the remaining are message positions. Okay. So, if you do 8-4 code, reliability sequence is 1, 2, 3, 5, 4, 6, 7, 8. So, the frozen positions are 1, 2, 3, 5. Okay. The message is 4, 6, 7, 8. Okay. So, how do you visualize the polar code construction? You can go back to the binary tree representation of the polar transform. Okay. And 1, 2, 3 and 5 you set as 0. So, this is all frozen. Okay. I will write F here to indicate that these are frozen, and then write M here to indicate these are message. Okay. So, the first, second, third and fifth leaf nodes are frozen to 0, the remaining are set to M1, M2, M3, M4. Now, how will this encoding happen? You will do 0 here, 0 here, and you will get a 0, 0 here, right. 0, 0 goes to 0, 0. You get 0 here, M1 here, and you will get M1, M1 here, right. So, 0 is coming here, M1 is coming here. So, 0 plus M1 is M1, then M1 itself is retained. Here likewise you have 0 M2, so this will be M2 M2. Okay. This is M3 M4, so you will have M3 plus M4 M4. Okay. Then what will happen in the next step? This is 0 0 M1 M1, so this 4-bit vector will be M1 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 M1. This will be M2 plus M3 plus M4, M2 plus M4, M3 plus M4, and then M4, right. So, that is what happens at this node. You combine M2 M2 and M3 plus M4 M4, you take the XOR of these two, keep it here, and then this is retained as it is. Okay. So, remember this is retained as it is, the XOR of these two goes here. Okay. That is what happened in this. And then finally, the code word, 8-bit code word is going to be again XOR of these two, and then this retained as it is, right. So, let me write it out laboriously for you. M1 plus M2 plus M3 plus M4, M1 plus M2 plus M4, M1 plus M3 plus M4, M1 plus M4, and the remaining 4 are the exact same things as this: M2 plus M3 plus M4, M2 plus M4, M3 plus M4, and M4. This is the encoded version. So, this is the input to the transform, and this is the output of the transform, and that is the code word. Okay, so, this is the code word. Okay. So, you have a message M, which is M1, M2, M3, M4. M is M1, M2, M3, M4, and the code word is this. Okay, remember, plus again is XOR or modulo 2 addition. You do all these things. Okay. So, if you want, you can create a generator matrix out of this. You will get, this easily specifies the generator matrix. Okay. You can construct that if you like. Okay, you will get a 4 by 8 generator matrix, and you notice this is not a systematic encoding. Isn't it? M1, M2, M3, M4 does not appear by itself in the code word. It is not systematic, but this is the encoding that you have. Okay. So, once you fix length and the number of message bits, and once you have a reliability sequence, you can always do polar encoding, and this tree representation gives you a very simple way in which you can implement the encoding as well. I am going to give a few more examples. Here is a 16,10 example. Okay. So, for n equals 16, the reliability sequence is this, and you have to freeze the first 6 positions, right. So, first 1, 2, 3, 5, 9 and 4 will get frozen. In your tree, you have 16 leaf nodes. The first node, second node, third node, fifth, fourth and then ninth are going to be set as 0. The message will go into the remaining place, and then you will start encoding as before. You will get the code word at the output. Okay, the code word, each bit of the code word will be some XOR of some M1, M2, M3 like that. If you want, you can write out a generator matrix for that, and you have the definition for a 16,10 polar code. Okay, the same thing happens for 32. Okay, there is nothing different about it. N equals 32. So, and 20 is the K. So, you have to freeze the first 12 positions. You go all the way up to 11. So, what are the frozen positions? 1, 2, 3, 4, 5, 6, 7, and then you have 9, 10, 11, 17 and 18. Okay, so some sort of numbers there. They get frozen to 0. Remaining have the message bits. Once again, you can combine and create a generator matrix if you like. Okay. So, in fact, viewing the freezing as in U times Gn is also quite easy. Okay. So, this is the polar transform. You look at the non-frozen positions in U and the rows corresponding to Gn and that will give you the generator matrix. Okay. So, that is a quick way to come up with the generator matrix for the polar code. Okay. So, this is example, and here is for 16,10 a full blown binary tree representation. I am not going to go through and show you the computation, but this is what happens. You have frozen bits 0 and then the message bits 10 of them, and they combine and you create the 16-bit code word. Remember, once again, these are all 1 bit here, these are all will be 2 bits, right, and then you have 4 bits, then you have 8 bits here, okay, and then finally you will have 16-bit code word. Okay. So, that is it, that is the polar code. And even if you have a, so you can imagine if you have n equals 1024 and k equals 512, what do? Okay, you go back to that big slide I showed you. Okay, this is n equals 1024 and k equals 512. What will you do? You take this big vector and then mark out the first 512 positions and make them frozen, and imagine this tree, and on the leaf you freeze all of them, set them to 0, put the message bits in the remaining places, and then do the encoding. Okay, I mean, it's hard to do it by hand, but you can write a quick program and that will work quite fast. Okay, so that's the end of the description of the polar code. Hopefully this was clear to you. Once again, the important things to focus on are the polar transform, this notion of bit channels, how we define them, and how the reliability sequence is defined. That's very, very crucial. And once you have a reliability sequence, you have a polar code. Okay, once you have it for any n, it is a polar code. Okay, so n comma k polar code. You have frozen positions and message positions. You freeze the first n minus k, and you put your messages in the remaining k. Okay, that's the end of this lecture on polar codes. In the next lecture, we will see MATLAB programming for writing a quick encoder. Once again, we will write a very simple and encoder that works for doing the polar encoding. Okay, thank you very much.